Hello students, welcome you all. Now today I will tell you how to construct the pi molecular orbital diagram of allylic system, that is odd carbon systems. In my previous lecture I told you how to construct the pi molecular orbital diagram of a conjugated system, or simplest system that I told you, that was the ethene, then butadiene, then hexatriene, and then the octatetraene. And I told you how to some of the rules to draw these molecular orbital diagrams. Now let's see the molecular orbital. So that were the molecular orbital diagram of even carbon systems. The ethene containing the 2 carbon, butadiene containing the 4 carbon, hexatriene 6, octatetraene 8, like this. So that were the molecular orbital diagram for the even carbon system. Okay, now let's see how to draw the molecular orbital diagram for the odd carbon system, and we will see for the allylic systems. Okay, now if you will see this allylic system, or so suppose this is either allylic cation or allylic anion that we can see. Okay, so this, suppose this allylic cation. So allylic cation containing the 2 electrons. In the same way, this allylic anion containing the 4 electrons. And this is 3 carbon system. Okay, in the same way, we can have the 5 carbon allylic system, or we may have the 7 carbon allylic system. So this is 3 carbon allylic system. In the same way, you may have the 5 carbon allylic system, and we may have the 7 carbon allylic system, like this. Okay, so these are the allylic cations, and in the same way allylic anions. So how we can draw it? So some of the rules. So for drawing these molecular orbital diagram, we should know some rules to draw it. So previously I told you some of the rules to draw the molecular orbital diagram. Some of the rules are common here also, and some new rules are also there to construct easily their molecular orbital diagram. One of the things that what I have told you in my previous lecture, I told you if there is two atomic orbital, then they will combine and it will give you the 2 molecular orbitals. If 4 atomic orbitals are there, they will combine and they will give you the 4 molecular orbital. And likewise, if 8 molecular orbitals, if 8 atomic orbitals are there, they will combine to give you 8 molecular orbital. In the same, and out of that, half were the bonding molecular orbitals and half were the anti-bonding molecular orbitals. So here in allylic system, these are the 3 carbon system. So here also, if we have 3 atomic orbital, 3 carbon systems, then number of atomic orbital, molecular orbitals formed, that would be also 3. So 3 atomic orbitals combined together, or odd molecular orbitals combined together to give you the same number of molecular orbitals also. Okay, so odd atomic orbitals combined together to give the same number of odd molecular orbitals. So one of the rules that odd atomic orbitals combine to give same number of odd molecular orbitals. Okay, and now out of this, if there are 3 molecular orbitals formed, then out of this 3 molecular orbital, 1 would be bonding, 1 would be anti-bonding, and the middle or molecular orbital will be the non-bonding molecular orbital. In the same way, if 5 molecular orbitals are there, then out of 5, 2 lower will be bonding, 2 higher, that is highest, at the highest energy state, that would be anti-bonding, and middle one, that would be the non-bonding, and so on. So out of out of odd molecular orbital, out of all odd molecular orbitals formed, half are bonding molecular orbital, half are anti-bonding molecular orbitals, and the middle one will be non-bonding molecular orbital. Non-bonding molecular orbital. Okay, so this is the second rule. Okay, and same rules like before. The first molecular orbital will have the 0 node, second will have the 1 node, third will have the 2 node, and like this. So same rule like before. So for psi n molecular orbital, the number of node will be psi n minus 1. Okay, and next one, the important one. So the middle non-bonding. So what about the nodes? So how we can draw the nodes over here? That is the important point. If we want to draw the nodes in middle or non-bonding molecular orbital, then where should we draw the nodes? Where we should put the nodes? So for non-bonding molecular orbital, all nodes passes through the carbon atom, or you can say, or passes through the orbital, passes through the carbon atom, That is, suppose if these are the 3 carbon atom containing the orbital, okay, then this is the node which is passes through the carbon atom, and these 2 are the nodes which are passing in between the carbon atom. So for non-bonding molecular orbital, all nodes passes through the carbon atom. So this is for the non-bonding molecular orbital, and in any molecular orbital diagram for this allylic system, you will have only one non-bonding molecular orbital, which will be present in the middle. Now, so this may be this non-bonding molecular orbital, and that would be your even molecular orbital otherwise. Now for the rest of the even molecular orbital, so this is always this non-bonding, that would be the even molecular orbital in case of odd carbon systems. So this is allylic system or odd carbon system. Okay. Now for other even molecular orbital, so this will be the middle even molecular orbital, which is the non-bonding molecular orbital. Now for other even molecular orbitals, now I am talking about for other even molecular orbital, this will also be the even molecular orbital, but for other even molecular orbital, for example, it may be psi 2, it may be psi 4, it may be psi 6, but except non-bonding one, except non-bonding. So for other even molecular orbitals except non-bonding and molecular orbitals, the first node that would be passes through the carbon atom, and the rest of the node that will be passes in between the carbon atom. So for even non-bonding molecular orbital, the first node passes through the carbon atom. Through the carbon atom. Through the carbon atom means this is through the carbon atom. In between means in between these two carbon or in between these two orbital, the node is passing here. So the first node passes through the carbon atom, and rest of the other node and rest of other node passes in between the carbon atom. The carbon atom. Okay, this is the thing. So this rule for non-bonding, this rule for even molecular orbital, and next rule for odd molecular orbital. So for odd molecular orbitals. Okay, for odd molecular orbitals, no doubt the first molecular orbital doesn't have any node. Okay, so for odd molecular orbitals, for example, it may be psi 3, it may be psi 5, it may be psi 7, and so on. So for odd molecular orbitals, all nodes passes in between the carbon atom. In between the carbon atom. Okay, so this rule that we should remember while drawing the molecular orbital diagram for the odd carbon system or allylic system. Okay, so these three are the main rule for non-bonding molecular orbital, for even molecular orbitals, and for odd molecular orbitals. These three rules that we should keep it in mind. Okay, now let's see the simplest molecular orbital diagram for the 3-carbon system, and this is suppose 3-carbon system or allylic system, or we can say the allylic cation, we may say allylic anion. So 3-carbon system. Okay, so for this 3-carbon system, if you will see, the number of carbon atom is 3, number of carbon atom of p orbital is 3, and number of this molecular orbital will also be 3. So here if you will see, number of carbon atom or p orbital, or we can say p orbital, is equal to 3. So therefore number of molecular orbitals formed will also be 3. Out of 3, 1 will be bonding, 1 will be anti-bonding, and the middle one, that would be non-bonding molecular. Now let's see, it's a molecular orbital diagram. 3 molecular orbitals would be there, psi 1, psi 2, and psi 3. Okay, now what about nodes? Number of nodes, psi 1 means 0 node, psi 2 means 1 node, psi 3 means 2 node. Okay, this is the first molecular orbital, lowest molecular orbital. Always they have the positive sign. All loops have the positive sign. Last molecular orbital or the highest energy molecular orbital, they always have the alternate sign, plus minus like this. So this is the odd molecular orbital. So in odd molecular orbital, what I told you the rule, the end orbital has the same sign plus plus. This is also odd molecular orbital, end orbital is having the same sign plus plus. So number of nodes should be 2 here. So one of the node you can see, this is one of the node, this is the another node. So what I told you, for odd molecular orbital, in case of allylic system, for odd molecular orbital, all nodes pass in between the carbon atoms. So here you can see this node is passing in between the carbon atom. Okay, except this psi 1. So I have written psi 3, psi 5, psi 7, not psi 1. Because psi 1 doesn't contain any node. If any odd is containing the node, then that should pass in between the carbon atom. Now this is the non-bonding molecular orbital. This is our non-bonding molecular orbital. So for non-bonding molecular orbital, if you will see, then this is having the, what is the rule for non-bonding molecular orbital? All nodes pass through the carbon atom. So this is non-bonding, psi 2 is non-bonding here, number of node is 1, and that node should be passed through the carbon atom. So only the center. So through the center is, this is the p orbital, and we should not draw this p orbital over here because one of the node is present over here. So this is plus and this would be minus. Even molecular orbitals, what I told you, the end orbital should have the opposite sign. One is plus and another is minus. So like this we can draw for this one. Okay, now if you will see the these are the nodes, and if we want to see the symmetry in this orbital, okay, so sigma symmetry, if you will see sigma symmetry, then this psi 1 is symmetric with respect to C2. As you can see, suppose one of the mirror plane passes through the center, then in front of plus sign you will have plus sign, in front of minus you have this minus, like this. What about this psi 2? Whether psi 2 is symmetric? No. So in front of plus in the mirror, plus should be there, but here it is minus. In front of in mirror plus, then minus, that's why it is anti-symmetric. And here if you will pass the mirror plane in from the middle, then in front of plus you will have the plus, that's why it is symmetric. So what about this C2 here? What about this C2? So if you will rotate by 180 degree, then this and these two, this will come here over here, this will go over here. So in place of plus, so this will come over here and this will come over here like this. So that's why in place of plus you will have minus, and in place of minus you will have plus, like this. So that's why it is anti-symmetric with respect to C2. What about this? What about this? In place, suppose if you rotate it by, suppose if you rotate through this axis by 180 degree, then what will happen? So this plus will go over here, and this and this minus will go over here. So it is symmetric with respect to C2, and this would be the anti-symmetric with respect to C2. So like this we can draw the molecular orbital diagram for the odd carbon system or this 3 carbon system. So let's see for 5 carbon system. So for 5 carbon system, allylic system, okay, this is suppose 5 carbon allylic system. So number of molecular orbitals formed, that is equal to 5. Number of molecular orbitals formed, that will be equal to 5. Okay. Now, so 5 molecular orbitals, and we can name it as psi 1, psi 2, psi 3, psi 4 and psi 5. Now according to this rule, what I told you the rule, the first molecular orbital, either allylic system or even carbon system, all lobes have the same sign, plus, 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 plus. Now for psi 2, now come to the last one. All orbitals have the opposite sign. All orbital having the opposite sign, plus, minus, plus, minus, plus. Okay, and end orbital should have the same sign. This is odd molecular orbital, end orbital is having the same sign. Now come to the non-bonding molecular orbital. So this is, third one is the non-bonding molecular orbital. This is non-bonding molecular orbital. So for what is the rule for non-bonding orbital? All nodes passes through the carbon atom, and number of nodes, if you will see number of nodes here is 0, 1, 2, 3, 4. So for third, which is the non-bonding molecular orbital, the nodes, number of nodes is 2, and this should pass through the carbon atom. So the only possibility, if you will see, it cannot pass in the middle. Two nodes cannot pass through the middle. In case of two nodes, when the node is even, if the number of nodes is even, then the nodes should not pass through the center. So the only possibility left over here, this is the two nodes that can be passed over here through the carbon atom. Okay, so this is odd system, this is odd molecular orbital. No doubt the end orbital is having the opposite sign, and if this is plus, then this should be, this is plus, end orbital having the same sign. End orbital is having the same sign for odd molecular orbital. If this is plus, then that should be minus, this is plus. Okay, now come to the psi 2. Now psi 2 is the even molecular orbital. So no doubt the end orbital should have the opposite sign. Okay, end orbital is having the opposite sign. And what is the rule for this even molecular orbital? This is for even molecular orbital. Okay, the first node passes through the carbon atom, and rest of the node passes in between the carbon atom. So first node, this is the first node that should pass through the carbon atom. This is the first node passes through the carbon atom, and next node, we cannot write the next node over here, this one or this one. So next node will come, no doubt, the next node will come at this place. So if this is plus, then this is minus, and if this is minus, again node is present, then that should be plus, and node is all present over here, so plus minus. Okay, this like this. Now come to the psi 4. What is psi 4? Is even molecular orbital. So psi 4 is the even molecular orbital. So again same rule, the first node passed through the carbon atom. So number of node is 3. So first node passed through the carbon atom, and rest to pass in between the carbon atom. So so here the nodes pass, only one node is present. So what should I write here? Please correct it. So this is plus, minus, okay, and this is minus, this is plus. Half is plus, half is minus, always in the second one. Okay, now for psi 4, 3 nodes are present. One of the node will pass in between the carbon atom, and rest of the nodes, no doubt, it will not pass through here. It should pass from here. So if this is plus, then because this is even, so end orbital should have the opposite sign, and then this should have the minus, and this should have the plus. So this is the diagram, molecular orbital diagram for the for 5 carbon system. And we may also write its symmetry, sigma, and C2 symmetry. If you want to write, we can write the sigma. So sigma, this is symmetric, AS, start with S, SA, SA, S. If you will C2, start with you may start with A, S, A, S, A. So you may check the symmetry by putting the mirror plane over here, or by drawing one of the axes in the middle. So you can check whether it is as before that I have seen. So you must see the previous lecture where I have shown the model to understand the symmetries in these molecular orbitals. So this is for 5 carbon system. In the same way, we may draw for the 7 carbon system. So 7 carbon system, either it may be allylic cation or allylic anion. So for 7 carbon system, if you will see, so number of molecular orbital formed, that is equal to 7. So you may draw 1, 2, 3, 4, 5, 6, 7 like this. Okay, so like this. So this is psi 1, psi 2, psi 3, psi 4, 5, 6, 7. Now see nodes. Nodes here 0, 1, 2, 3, 4, 5, 6. Now first molecular orbital, no doubt, all should have the plus sign, plus, 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 like this. Last node, highest molecular orbital, having the opposite sign, plus, minus, plus, minus, plus, minus, plus. Now come to the middle node, that is the non-bonding molecular orbital. So this is the non-bonding molecular orbital. So what is the rule for non-bonding molecular orbital? All nodes pass through the carbon atom. So all nodes that should pass through the carbon atom, and this is the even molecular orbital. So for even molecular orbital, what I told you, the end orbital should have the opposite sign. The end orbital should have the opposite sign. And the 3 nodes that should pass in between the through the carbon atom. So this, no doubt, the first that should pass through in the middle, and next you should pass from here. Okay. Then suppose if you draw, we cannot draw the node here. We cannot draw the node over here, because two nodes can't be in the neighbor. Okay, so that's why this is plus, this is minus, this should be plus, this is minus, like this. This is the only possibility which is left. So now come to the second one. In second one, because this is even, then the end orbital should have the opposite sign. And for the second molecular orbital, in all the molecular orbital diagram you have seen, half is having the plus sign, another half is having the even, another half is having the minus sign. And this is even molecular orbitals, and as you can see, the even molecular orbital, the first node passes through the carbon atom. So only one node is present. That's why this node that should pass through the carbon atom, this is the only one node which is present. So half is plus, rest half is minus, like this. Now come to the third one. Okay, now come to the third one. Now third one is the odd molecular orbital. Third one is the odd molecular orbital. Number of node is 2. For odd molecular orbital, the end orbital is having the same sign. First draw this 2, put this sign first, and then number of node is 2. We have to put the 2 nodes. So what is the rule for odd molecular orbital? Like psi 3, psi 5, psi 7, all nodes passes in between the carbon atom. That does not pass through the carbon atom, in between the carbon atom. So we should, how many nodes that we should draw? 2 nodes. No doubt it will not pass through the center. It will pass in between the carbon atom. So this is first and this is second, like this. Okay. So put it sign plus, here minus, 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 plus. Now, suppose if you put the node over at this place, suppose, then you will not get the symmetrical distribution. Suppose I put the node over here, or I may put the node over here. Suppose 1, 2, 3, 4, 5, 6, 7, and suppose this is psi 3. Suppose this is your psi 3. So we have to put 2 nodes. So I can't put node here. I have drawn the node over here. I cannot put node over here. So while this is not the symmetrical distribution, so if it is plus, then this should be minus, 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 minus. So 5 is having the minus sign, 2 is having the plus sign. This is not the symmetrical distribution. So only this will give you the symmetrical distribution. In the same way, I cannot pass the node, I can't pass node from here. If I put the node over here, then this should be plus, plus, and this will be plus, plus, and okay, and this should have the minus. So only one minus sign are all having the plus sign. This is also the symmetrical distribution. So distribution should be symmetrical, then only you will get the correct representation. So this is the thing. Now if you will see psi 5, then where this is odd molecular orbital, so the end orbital should have the plus sign, same sign. Number of node is 4. So where we should put the node? No doubt, if there is node is even, then we can't put the node in the middle. So node should be in between. So for odd, all nodes pass in between the carbon atom. So where we should put the node here? Okay, so I can put the node either this is 1, 2, 3, 4, or some other distribution you will see. So I may put the node at this place. Okay, so this is this one, and then this one, and then this one, like this. So here 1, 2, 3, 4 nodes. So if you will see, this is giving the symmetrical distribution. This is minus, this would be plus, this would be minus, and this is minus, like this. And if you will put the nodes at other place, then you will not get the symmetrical distribution. You will not get the symmetrical distribution. This is the only thing that you can see. This is the only thing that you can see. Okay, suppose if you put the node at these two in the node here, then you will not get the symmetrical distribution. This is the symmetrical distribution 1, 2, 3, 4, 1, 2, 3, and otherwise the distribution that would be not symmetrical, not so much symmetrical. Now next one, this is even molecular orbital, plus, minus. Okay, end orbital have put the sign plus, minus, different sign. 5 nodes, as this is even, so for even, first node pass through the carbon atom, rest node pass in between the carbon atom. So first node that should pass through the carbon atom, like this, and rest of the node pass in between the carbon atom, this one, third, fourth, 5 node. I have shown the 5 node. So plus, minus, minus, and this is plus, this minus, like this. So in this way, we may draw the molecular orbital diagram for the odd carbon system. If you want to see the symmetry, then you can write the symmetry. Symmetry you may write. So sigma, for sigma this is symmetric, asymmetric, symmetric, asymmetric, symmetric, asymmetric, symmetric. And for this C2, for C2, this is asymmetric, A, S, A, S, A, S, A, like this. Okay, so this is about the how to construct the molecular orbital diagrams. So this will help you in when I will discuss the electrocyclic reaction. Before you go through the electrocyclic reaction, you should be very much clear how to draw the molecular orbital diagram, what should be the HOMO here, what should be the LUMO here. So suppose if you see the HOMO, so what should be the HOMO? So here number of, if you want to fill the molecular orbitals, then let me fill how many electrons are present? 6 electrons are present. So 1, 2, 3, 4, 5, 6. So HOMO here is the psi 3 is the HOMO here. Psi 3 is the HOMO and psi 4 is the LUMO. So this would be the HOMO. This would be the HOMO, highest occupied molecular orbital, and psi 4, that would be the LUMO, lowest unoccupied molecular orbital. So in the same way, we can write the HOMO or LUMO for the other odd carbon system. Okay, so thank you. In my next lecture, I will start the electrocyclic reactions, the detail of this electrocyclic reaction. Okay, thank you.